All right, hey guys, this is Tom here with the presentation that we did the other day in our info sharing session. It's a presentation that Guise and myself have put together, and I've narrated it here for the people that couldn't come to the info sharing session. So it's one big presentation, but this is just part one of three. We're splitting it up over a couple of different nights to keep the night at about an hour and a half. And I think once I narrated this presentation, it will come to about an hour or so. So hope you enjoy it and let me know what you think. Cheers. We're splitting the big presentation up in three different sessions. The first two, you can see the topics here. We will start off with first of thermal theory and thermaling. So how to visualize a thermal, basically. How do they form? What do they look like? What does it look like on the hill? And what can you learn from that? And then obviously, like, where will you find them? What are sources and triggers? Where can you expect a thermal to go up? In the second presentation, which we'll do in the next month or so, we'll focus more on cross-country flying, in particular, how to prepare a flight, how to set up, how to plan a flight, after looking at the weather, how to set up your instruments, which we'll actually try to do on a separate evening altogether. I'll get to that in a sec. And then a bit more and specifically like takeoff timing, getting off the hill, what time of the day is best, etc. So this first presentation is really geared around more in general thermals and thermaling. Part of cross-country flying is obviously like all the gadgets that we use and the instruments that we use. So we want to do that in a separate evening, do a bit of a presentation on how we've got it set up, what you can see on the different instruments, obviously fairly limited to the instruments that we use. And I might change this presentation a bit, maybe with some of the new information on the Audi that Guise is using. But I use Fly Sky High, so I'll go through like how I've got it set up, what I'm looking at airspace, how to get that loaded on there, looking at live tracking, Live Track 24 in particular. So that tracks you, sends your information like onto the internet, so anybody can watch you fly and find you at the end of your flight, as long as you've got cellular reach, that is. Looking at waypoint routes, the retrieve WhatsApp group, for those that are not set up with that, we can set you up with that. And then like the setup of the radio, going over tone squelch, those type of things. So anything having to do with gadgets, we've planned to do on like a separate evening where anybody can bring in all their stuff. We can all get it set up and get you ready for your first flights. So there we go, thermals and thermaling. As I said, we fly from our only inland side here in Western Australia, Mount Bakewell, to be seen on the picture here, and everything behind it and around it is pretty much flatlands. So that's where we're flying, and most of this presentation will deal with that. So like, I'm not going into how to fly in the mountains and all of that. So if you're watching this on YouTube and you ended up here and you're looking for that kind of information, you won't find much. But yeah, let's get into it. So a couple of quick things we want to say. In general, like on this presentation, the goal of it, as we said, is getting you to visualize and understand how thermals form and what they can look like. And looking like is obviously a weird way to put it, because you can't see them, which is why you need to visualize them. But if you do have an idea or a sense like what they can look like or would look like if you could see them, then you can make more sense of your flying, and obviously take your advantage from that and fly further and stay in the lift longer, etc. A quick note on how to start learning how to thermal if you've not done much, or if you're a fairly new pilot. Getting started at the end of the day, like at the end of the day around Mount Bakewell, we often get what we call magic lift, where there's pretty much lift everywhere. It feels like, anybody can stay up because the lift is so, it's just everywhere around. Instead of just flying around and just enjoying the view and And obviously that's beautiful to do if you just like to do that and want to cruise around. But it is a perfect time for you to actually try to do the actual thermaling. There's still thermals around. There's still areas where you can find more lift, and where you can put in practice the things that we will talk about in this presentation. So instead of, just floating around and getting some beeps here and there, like getting some lift and then flying through it and go to the next and, tap yourself on the back because you flew like just for an hour and a half, use that time to, like this time it's easy to stay up even if you lose the thermal, but try to stay in the thermals that you do find. So if you find some lift, start turning, do the turns and use the techniques that we will talk about in a bit. Once you are good at like staying in the thermals at that time of the day, then you can start, come back on other days and during the day where, if you lose the lift, you really have to find another one. Yes, it's not as easy to stay up. And then a quick note, we'll come back to that a number of times during this presentation, but like to understand what's going on, it is important that you realize that, even though you may go up in relation to the ground, you're always going down through the air. So if you're flying into a thermal, if the air in the thermal goes up by 6 meters per second, you only go up by, let's say, about 4.5 to 5 meters a second, because you're always going down through the air with a meter and a half per second. So, which means that if your vario says like, hey, you're flying in zero lift or you're not going up or down, it does mean that you're flying in air that's going up. So it's important to keep that in mind, because that will get you to understand like why you sometimes may lose a thermal or why not. So the first big sort of like general idea of like how do thermals form, I suppose everybody sort of gets this, but I'd like to give you like how I visualize this, and there's been a number of different ways that you can sort of like imagine this, but this is the bit that I use. I look at a field, for instance, that generates heat as an upside down bathtub, as this picture here shows. So the idea is simple. The sun heats the ground, so the sun obviously like radiates on the ground. That radiation like heats up the ground, and the ground then heats up the air just above it. Okay, so you start to get a little bit of a bubble of hot air sitting on the ground, let's say on that field. Just because that air is a little bit hotter than the surrounding area, it doesn't make it go up just yet, because there might not be enough energy. It needs to have like a proper amount of energy sitting there before the air actually starts rising. So because air is mass is inert, so like it takes a certain amount of energy to get it in movement. So the hot air sits there and builds up. That's where I picture, so the bathtub gets fuller and fuller and fuller until it reaches a point where a threshold is reached at a certain point, and the plug pops out of the bathtub and we'll get some release out of that, like from that bubble through that plug, like going up. So why I imagine like sort of bathtub, as Volker was pointing out, like it's not like all that big bubble of air on that field will all release, all in one go. How Volker pointed out, like you can also imagine, instead of an upside down bathtub, you can think of like when you shower in your when you're taking a shower and the steam sort of like rises to the ceiling and starts to become like drops there. All those drops that are hitting on, like start to form on the ceiling, they don't fall down from like one specific point, like, or from all points at the same time. Like they come down at sort of either the lowest point or somewhere where there's a bit of like inconsistency in the ceiling. And it's the same on a field, like that bubble of air will start to release from the point where where it releases, but it's not all at the same time. So when that release happens, and at least the minimum sort of amount that this air needs to be hotter than the surrounding air for it to actually have enough energy to start rising is about 2 degrees difference. So that air needs to be 2 degrees hotter than, you know, just the surrounding air. Then it goes up. Then it's the question of like, hey, like, is there enough heat in this bathtub to, like, when it starts emptying through that plug, does the sun heat up that field fast enough for this to become like a continuous stream? Now, generally early in the day, you'll find that the sun is not yet strong enough to replenish that heat, and you get a release, a little bubble, the bathtub emptied, and the sun needs to first build up that bubble again before another bubble releases. So in the morning you get sometimes quite like aggressive little bubble thermals rather than a nice big continuous thermal. Now this hot air then, when it goes up, it rises until it reaches an area where the surrounding air is of the same temperature. So we'll get to that back to that in a sec, but you know, when you go up in altitude, the temperature drops, but it doesn't. The surrounding air might have different layers of different air temperature, and that thermal will go up until it reaches a point where that air temperature is the same as where the thermal is, and then there's no more energy for it to go up further. So a couple of things to say about, you know, that picture and those thermals. First of all, in protected areas, air can build up hotter before releasing. So, you know, when that release happens, it really is a function of, like, if anything, like how easy it is for the wind to maybe push up that bubble onto like a row of trees, how easy it is for, maybe there's like sheep running on the field that like throw up that bubble a little bit, and because it rises a little bit, it keeps on going. But if it's sitting, let's say there's a field surrounded by trees, and or even, let's say, a car park where the air is pretty still in between the cars that are parked, if there's nothing happening, that air can build up like a bubble of air that's quite a bit hotter than that 2 degrees difference. It can kind of stick on the ground quite a bit longer. As I already said, if that area, that bathtub, is big enough and heats up fast enough, it can at some stage it can sustain a constant flow of hot air to keep the thermal going. Otherwise you have bubbles. If there's prevailing wind, so if there's wind blowing onto, you know, through that area, while the thermal can then be blown, like we'll get to that, like can start angling, but also can start to move. If there's more, you know, more bathtubs and more sources downwind from the thermal, there's a good chance that thermal will go on the move and slowly will move across the land, sucking up hot air from different sources. Also, this picture, you can imagine, like if there's like a field here and a field like a bit further away, they will have their own like smaller sources of thermals going up, but at a certain height those thermals, you know, might join up, get together, and you generally see that like at a certain height, like when you get higher up, thermals will become bigger in size, will become stronger, just because we've got thermals joining up together. And then a point to make, which will become like obvious why that's important: a thermal is heavy, so air going up, that mass of it moving up, the prevailing wind will go around it, will not like blow through it, it will actually go around that column of air, and only move it like very, very, very slow. Alright, then the next question is, how high will these thermals go? So in my last presentation that we did on weather apps and how to read the weather, I've gone into how to read a sounding, which you see a picture of here. Quick repeat of a small bit of that, a bit more information in the other presentation. So for those who haven't seen that, the red line you see in this graph here is the temperature as set out against the altitude. So this being close to Bakewell, the ground is about 221 meters up, as you can see. Let's see if I can get my laser pointer on. So that's where ground level is, and the temperature at ground level, as you can see here, is about 17 degrees Celsius. And then when you go up, you can see that the temperature is predicted, because this is a forecast, is predicted to drop relatively fast first, then a little bit less fast, slower, and then from about 2,000 meter to about 3,000 meter, that looks to be like an inversion. Inversion meaning that the temperature of the air actually goes up with altitude. So, so that's one thing you can read here. So as I said, this is a forecast, but you could get this sort of line if you in actual temperature, if you just let a balloon up and you just measure the temperature going up, which is what they do, and then they interpolate that and extrapolate that like into the future and give you for a certain time in the day what they think the layers of temperature will do in the air. Another important thing that for this conversation we need to have a look at is this gray line. That's a dry adiabatic lapse rate, which basically the only thing you need to know about that is how fast does a bubble rising from the ground, how fast does that drop in temperature. That's a steady rate. So that rate is about 1 degree per 100 meters. So with those two little bits of info, we can have a look a little bit more detail if we can determine how high the thermal will go. First off, as we discussed, a thermal will not start rising until the difference with the surrounding temperature is at least about 2 degrees. So if the surrounding air is supposed to be 17 degrees, the air from the thermal before it starts rising should be about 19 degrees. And then, as I said, it starts dropping at a rate of 1 degree per 100 meters, which is this blue dotted line. So now you've got the temperature of the thermal at every different height. So you see that first is the difference in temperature might be 2 degrees, but like at a certain height, like let's say up 1,000 meters, that difference might be 5 or 6 degrees, which means that the thermal at that point has a lot more energy, a lot more buoyancy. So that's why you get like sort of in the middle part of those of your lift, you get often stronger bits of lift. Now once it gets closer to the top of the thermal, or like closer to the surrounding air being at the same temperature, and here you can see that at around about 2,000 meters, this thermal will reach the same temperature as the surrounding air, which means there's no more energy left for it to rise, and that's where the top of lift is. We often call that cloud base, but it's not always the same. Like obviously there's thermals if there's clouds or not, and you can't always get to the clouds, but just generally if we be talking about cloud base, we actually talking about top of lift. And sometimes you can't get to the clouds, because if those last couple of 100 meters, for instance, if they have rising air that's only going up by 1 meter a second because there's not much energy left, then you'll find that like because you're still going down through the air with 1 meter, 1.5 meters a second, the air goes up by 1 meter a second, but you can't actually get up higher. You can't actually get closer. So those two things are related, but not the same thing. Then one last quick thing, since it was still in there, you can, with that same technique, you can look at like, okay, how cold would it be at the top of your lift, at the top of your thermals. So then you can get a bit of an idea of how warm you need to dress. So with the information we just spoke about, like how thermals form, you can start theorizing and like seeing why thermals in summer are often bigger, stronger, and more aggressive, because the temperature difference from night to day like happens a lot faster in summer. The sun rises faster, the sun gets up straight above the landscape like quicker, here in the flatlands, which means that that energy that a field gets is is building up a lot faster in the morning, and that difference in temperature, that's what we need to get thermals going. In winter, while it's colder, you still get a temperature difference. The sun still comes up, but if there's more clouds, obviously, like the temperature, like the sun's energy gets diffused a lot, so those temperature differences are sometimes very small. And if it's a blue sky day in winter, the sun doesn't come up as fast, it doesn't go up as high, so it takes a lot longer for a temperature difference to build up, which means that the thermals are generally weaker, and on top of that, the days are shorter as well. So the sun comes up later and goes down faster, so your days are shorter. So generally in winter you won't find record days, but there's definitely nice flying days in winter that you can find, and especially if you don't like to fly in very aggressive thermals, winter is definitely a good time to still go out and practice and get ready for summer. So what does a thermal look like? Now this picture, which I stole from somewhere online, so if you own this picture or you made it and you'd like to get credit, definitely let me know. I'm happy to put it in the comments somewhere, but this is just an idealized version of like what a thermal looks like. In reality, it's hardly ever as clean as this, because as we've already seen, instead of like this one big column that starts from like a big area on the ground, you generally have some smaller cores that that start from the ground and then that join together a bit higher up. But this is just to show you kind of what the air around these thermals do. So in nil wind, the left hand side picture here, you see like hot air going up, and outside of the thermal there's air goes down, so you've got sinking air. So if you're flying up to a thermal coming from any type, if there's no wind, so there's no downwind, but you'll find that you get increased sink first before you hit lift. And then obviously if there's enough moisture in the rising air, and if it gets high enough and cool enough so it reaches the dew point, which is obviously a function of like how much moisture is in the air in combination with the pressure in combination with the temperature, then you either get clouds or not. So, but if there are clouds, cumulus clouds do form because thermals reach like the underside of it. So clouds are definitely a good indication of where you find a thermal underneath it. So if there's more wind, more prevailing wind, as we said earlier, a thermal has mass. Mass means like it's inert and the wind doesn't blow it very quickly, but a thermal can slowly move, like it can move that upwards air and it can redirect it a bit further downwind. But then the prevailing wind will hit that thermal mass and can actually ride up that thermal. So you can actually get a little bit of almost like ridge lift in front of a thermal. As I mentioned on the night, Rod has often said like, hey, like when you fly downwind, you often get a little bit of lift, then a little bit of sink before you hit the real core. And I think that might have to do with something like this. Like you get a bit of lift where the air gets sort of like deflected up, then you've got a bit of turbulence of where this shear happens, and then you actually hit the actual thermal. So if you fly into this and you start thermaling there, you're trying to do basically ridge soaring onto a thermal, and you find like, why am I going down every time I'm doing a turn and then going back up there? Like you feel like you're falling out of the thermal. Maybe it's a bit, and sometimes you leave it and you go a bit further downwind and they're like, hey, now I'm in the thermal. And again, on the back side of that thermal, you've got sink, which is why it's important later on that we, when we do our thermaling and we're actually going down through the thermal, but then drifting up with the air, that we keep pushing forward. But we'll get to that. So if you look at thermals from the top, especially here, which is a bit of wind is more likely, the faster air that's going up to the cores that have that are stronger, they got like more mass, or like at least more vertical acceleration. So they tend to sit, they don't get blown away as easily. The weaker stuff tends to gets pushed to the back more and more. So I'll get to another picture of that in a bit, but that's kind of what this top picture wants to show. Probably not really necessary, but I had this picture already, so I thought I'll pop it in. So obviously, when you're on Mount Bakewell with our launch over here, we're launching this way. Here's the race track, which you see right out front. Assuming we got a bit of a southern wind here. Then if you look at sort of the ground, so in this case, you would expect heat to build up in the sort of the darker fields or around the houses. Those thermals will get pushed by the wind, or that hot air, if the wind is strong enough, can get pushed by the wind, and they travel sort of along the bottom here and then run along the hill to the top and release from there. Which, if I look at a couple of my track logs, and these are some of my more successful flights, so I don't always get it up as high as this, but the point is, I wanted to show that I pretty much get my climbs out right from the top of the ridge. And if I look at it from the side, so if I switch from looking at it from the left hand side of this picture, but then looking towards the hill, so you get the racetrack here on the right, you see that we usually fly when the wind hits the hill, so the thermals are slanted back, and there's in different sort of wind speeds, you'll see very different angles of those thermals. So, just getting back to what those thermals look like. So, amazing graphics, I know. Not stolen this time, fully self-made. So, feel free to steal this. Just credit me for my amazing artwork. Top of the wing here, paraglider flying downwind. There's blue arrows. So you see when you come downwind towards the thermal, you first can experience some heavy sink. So you're already going down by a meter and a half a second, just gliding through still air. But because there's a thermal nearby, you get extra sink because of the thermal, other air going up in the thermal, so it's dropping down just outside it. So you get 2, 3, 4 meters a second down, so you're actually flying through sinking air. Once you get closer to the thermal, then I generally find my rate of descent drops, and that can be because the air is running up the thermal a little bit, and at that point I generally ease off the speed bar if I'm on speed bar, and get ready to start thermaling and find the lift. So just where that up and down air sort of hit the thermal, you can get a little bit of turbulence. And then, as we discussed earlier, because the weaker lifts get pushed towards the back a bit easier by the wind, you'll find that the core is sitting further out front. Now this is an idealized version with one core. Obviously there could be several cores, but the point is that the weaker stuff is generally more upwind than the stronger stuff is more upwind than the weaker stuff. If we flip this picture, then we get basically the situation how it is generally when we take off Bakewell. So if we got a takeoff on Bakewell on the right, and the little paraglider just launching, see it the paraglider launched at exactly the right time. Because what will this feel like on the hill? When you're standing over here, if there's no thermal, you've got the prevailing wind. You feel that wind. Now there's a thermal coming up. Just before that thermal hits, that air is sort of going around the thermal and is missing you on launch, and you'll find the biggest lull as you can feel. Now sometimes that's absolutely zero wind. Sometimes that's still a little bit of wind, and sometimes it's even, the thermal is sucking so much air up that the windsock on top of launch will actually point downwind. Now then, like if the prevailing wind is onto the hill, but in the lull the windsock is pointing downwind, there's like a fairly big thermal coming up, which is sucking the air up. So that's a good time to start getting ready, because once that little bit of the weak stuff from this thermal is traveling onto the hill and is standing there, so you're standing here and you start to feel that little bit of updraft, which will feel like extra, like starting wind, that's a good time to launch, because then you fly out and you fly through into lift, into more lift, into more lift, into more lift, into a lot of lift, and then you start feeling like, hey, now I'm flying through it, so then you can start circling. The later you take off, so the longer you wait for this to become stronger, 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 the quicker you launch. And now this core, instead of having it nicely out the front, you have it right on the hill, and you do a couple of turns and you're on top of the hill. So we'll get to that. So just remember that, because I'll get back to that in a little bit. Quick tip from Guise. It's the wind that drops, obviously is an important sort of factor, but at that time you can generally also hear more sounds from the bottom, because the thermal is blocking the wind. So if you notice, like, hey, I hear motorbikes from at the bottom drive around, it's generally because there's a thermal blocking it, and it's time to get ready. So, or if you've been on the hill for a bit, get a feel for the cycles, because a thermal will come through, then it drops, the wind drops, and then the next thermal will come through. So if you feel like, hey, the thermals take about this long, the lull is about this long, then you can time and you can get ready to take off at the exact right time to hit the next thermal. So that would look a little bit like this. So the thermal is blowing onto the hill. You start feeling, now it starts feeling a little bit of weakness. You take off, and you got a long time to work that thermal. If you took off later, you just have less time to work the thermal. If that thermal is not a continuous thermal, like this one, so if the side of the hill, there's no more air to pull up, then if you're in that thermal, you can ride it all the way up. But if the thermal ends, and you're towards the end, you always go down through the thermal, right? So if the thermal is has an end and there's a bubble going up, you will go down through the thermal. And if you're high up enough, you can get pretty high. But if you're fairly low in that, you might fall out of the bottom and have to make your way somewhere else. Takeoff timing. So when it's strong, so when the prevailing wind is strong, right, you kind of need those lulls that the thermal provides, like the drop of wind, just to take off safely. So if it tends to be a strong day, then you want to have a look, is it also looking like a day where the thermals are likely to be strong? Because if you get strong thermals, the lulls are bigger, and you can then you can take off in those lulls safely, get right out front of the hill, and make your way up. Because once you're in the air, it doesn't matter that it's strong. But obviously those days, if you're a less experienced pilot, you have to be very careful, because it's hard in strong winds to not get blown over the hill. And you want to definitely not find yourself in a position where you're in the air and wish you're on the ground. If the day is lighter and the thermals are still coming up the hill, because sometimes the wind is so weak that the thermals that are formed in fields down at the bottom, they don't even get blown onto the hill, and you're standing on the hill and there's no cycles. It's just dead. Now the only thing you can do then is, if the thermals don't come up the hill, is just launch, nice forward launch, fly out, and hope you catch one out front. There's nothing else you can do then. But if they do still come up the hill, but it's it's a bit weak, you also still want to launch into the start of the thermal, because you still want to use most of that thermal that's out there before it gets there. And last little point I wanted to make there, like sometimes like takeoff timings wise, if you have looked at the weather before, sometimes the prevailing winds is predicted to swing a certain way, which might not be very good for their taking off. So like if the wind swings, let's say very west after 12 o'clock, then it's important you take off before 12. All right, last thing on takeoff timing, and this was the most sort of important thing that I wanted to get to, and this is one of the things like I wish I had done different when I started flying, because the mistake I often made, like in hindsight, the mistake I often made was always waiting for the more experienced people around me to go first. Like let them launch first, and then when they launch and they look like they're going up, I'll go after. And what that means is that I often took off late in a cycle or later in the cycle, which gave the more experienced people more time to work the thermal, get up higher, get up above me. I had less time to work that same thermal and possibly falling out of the bottom or not getting it at all. So it is a bit of a trade-off. So if you go first and you bomb, as I said over here, if you go first and you bomb, the positive thing is the rest of the people will do the same thing as I did. Watch what happens with you. If you happen to have timed it differently and you go down and you end up back in loose paddock, it does mean that there's people looking at you, and probably somebody will come down and pick you up, and then they'll just wait for another cycle to come or for the day to pick up a little bit. But by then you've had an extra launch, an extra landing, and a little bit of airtime. So definitely worth going early. If you're first and you happen to do stay up because there's enough wind for you to just soar on the ridge, then you're already up in the air when the other guys, like the more experienced guys, launch. And if they catch the thermal, it's much easier for you to join them in that thermal when you're already on the ridge and maybe above launch height, than if you have to launch then and then join them. So in that case, it's also better if you go up first. As I already said, like if you're first, the earliest part, you've got the earliest part of the thermal. So you've got the longest time to work it. You can fly out further and the core will be further from the ridge, which means that it's easier for you to do your first 360s. Because if you catch that thermal very close to the hill, you'll find that in the strongest part you're too close to the hill to do a 360, and then you have to do like figure eights, and then maybe you don't you get drifted over the hill too quickly for you to actually work that thermal for very long. Look, you can stay on the hill and wait and see what happens with the other guys. Then if somebody catches a thermal further out, so if they fly out and they catch the thermal quite far out, hey, if you're ready to go, you can launch and then straight go out to like where they've got the lift. But I still think it's much easier to do that when you're already up. The positive thing, or like the reason that wait and see is like you would do that if you don't want to waste any energy by potentially bombing out, having to be brought back up. But generally, that would be like, now I would just not launch and see, only if I think that the day is not yet at sort of the ideal time for us to go. Like the cycles seem very weak, or if I look at the clouds, like the cloud base looks very low, then I might just say like I'll rather wait than launch and hope that I can stay up. But it's not based on letting other people go first. It's more based on I just want to go later. So in that case, if you're on the hill and they say like, hey, like we'll wait another hour for some good flights, I still would recommend doing a launch. Try to stay up as long as possible. Get a ride back up, assuming that there's people there with cars that can give you a ride back up, because you want to get those launches and landings in. So just my 2 cents. If you're fairly new to paragliding, and you want to get your amount of flights up. So we kind of already spoke about this, but a little animation here. So as I said, like if you launch towards a thermal, so the weaker stuff is sort of out the back, you can feel that it's coming. You launch early, you catch the core out front, and you can do your first 360s to get over launch height. At some stage you might feel like, hey, I'm getting a little bit blown over the hill. I'm not comfortable there. Then you can leave that thermal and like try to find the next one, but you get them further out front and higher. So it's not on the hill yet. These guys that like are waiting for this one don't feel anything yet, just wind still, but you're already up there. And like from there you can ride this one all the way up, or do the same thing for 2 or 3 or 4 more times before you catch like one that's nice and strong and gets you all the way up. The risk of trying to catch the first one over the hill is like, one, you might just lose it because of skill levels, which I always assumed that was the case. Like if I lost a thermal, and I've lost plenty, fairly low, and then I was like, oh, I'm not sure if I'm going to make it back at front of the hill, so I'll just run downhill and hope I catch another thermal there. But also you might just fall out of the bottom of that thermal. Like the thermal might just, you might just have made the most out of it as it is. And you can be the best pilot in the world, but if there's no more air coming up, then you're going down. All right, so we're getting to the thermaling. So this is a screenshot I took from, I'm pretty sure this is from an Andre Bandera YouTube video, and I will try to find the link to that video, because it's definitely a very good video to watch, and maybe even better than listening to me waffle and try to explain the same thing with less great graphics, because he's got like actually nice graphics to do to experience or to explain this the theory. But thermaling is very simple, and as I was saying yesterday to Volker, this is not one of those rules that like, oh, in the beginning you use this rule, and then like at some stage, like, you can do your own thing. It's different. I still do exactly this for every single thermal I'm doing. And while guys at the presentation yesterday kind of said at some stage like, oh, but sometimes I don't use it. If we talk more, like it comes out that he actually does use it, but he's been flying for so long, he does it all automatically. So let's say we're flying downwind, and like the wind thing here and the way the paraglider comes in, it's not really doesn't really match up. But anyway, so let's say I fly this way, and like I'm coming from like sync or not much happens to, I'll fly into my Vario starts beeping. So my Vario now starts beeping. I'm going up, and I'll find that I'll wait a couple of seconds, and then hey, there's enough for me to turn in. So I'm going to start turning now. You can turn left, you can turn right. In this case, obviously right is the right choice, but sometimes you don't know exactly. In this case, like if you fly this direction, you might feel that your right wingtip get lifted a little bit more, so you feel a bit of a tug on your right riser, which would make you feel aware like, hey, the lift is probably on my right. But even if you guess wrong, the theory works out the same. But let's say for argument's sake that we guess right. There's only two basically rules that you need to follow. If the Vario starts beeping faster, so if you're going into the right direction, you make your turn a little bit straighter. And if it keeps on increasing, you make it a little bit straighter. If it keeps on increasing, you make it a little bit straighter. And if the Vario starts slowing down, you make your turn tighter. And if it keeps on slowing down, you make it tighter. And if it keeps on slowing down, you make it tighter until a point where it either stays the same, then you keep that bank angle, or you keep that turn until it either goes faster or slower, and then you either straighten out or you tighten up your turn again. Which means that every time, so let's say I start turning the right way, every time I'm pointing towards where the lift is better, you'll find that I start increasing, the beep start increasing, So I straighten out my turn there. But because I'm still turning, straighten out my turn. And now like I'm actually flying away from, so I'm flying into, less lifty air, which is when I'm starting to increase my turn, so my turn gets smaller, and now I'm flying into the direction where it's going faster. So the beeps on my vario increase, and now they start slowing down again. So like I'm tightening up, and now I start straighten out again. So like the rule guides you slowly towards where the lift is highest, and you can always keep on doing that. So while you do that, that's a continuous process. Like even if you find the area where the most lift is, so in this case like 3 meters a second, let's assume that they mean you are going 3 meters a second up. Like that core moves with the wind. So like every time, like if you do like just a normal circle, the wind might blow that core further back, and now all of a sudden you're out front. So like you keep on using the rule to keep your adjustments going, so you drift with however the thermal is drifting. Again, watch that video of Andre Bandera, but this is like everything you see from here is just putting that rule into use. So just to let you know like what that would feel like, because you might now think like, doing 360s will feel like you're constantly, turning in roughly the same angle. It's like you're flying circles. When you're flying, like very often, it does not feel like you're flying circles, or the different parts of your circle feel very different. Now, a big part of that has to do with you having to push into wind. So you have to fly into wind a lot longer than you have to fly downwind. Because as we discussed, if you were to not adjust your circles and you would fly just circles, but you're going down through the thermal, that will mean like you actually fall out of the bottom of the thermal if you don't adjust your turns. Okay, so you have to adjust your turn to actually stay in that thermal, which means that your portion flying into wind is a lot longer, and like downwind and back into wind, downwind is a lot faster and into wind is a lot longer. And you need to do that so you stay in that column, and this whole column obviously moves up with you in it, but you still have to adjust to stay in that column. So what that looks like in this example, so this was like a week or two back when I was actually the only one launching on this day, because it was quite a strong day. Like one of those days that you really need a good lull on the start at launch for like the launch to be safe, and then you had to work pretty hard to stay in the thermal. So this left and right is the same thermal, just from different angles. So a little bit lower and angling, it actually looks like I'm doing like nice circles. But if you look at the same track log from above, you'll see that the circle is sort of into wind. I'm actually not going forward, like I'm just hanging into wind. I'm still going up, and you can't see that, look straight from above. But this little bit here, that actually takes probably about 10 seconds, where I'm hanging into wind. I'm slowly turning because I'm following the rules, and I'm flying into wind, and like that makes me fly through that strongest core. So I'm hanging there, and like once I flew through that core, which is now coming, downwind as fast as I'm flying through it. Like once I get through the end of that, then I'm turning, and this downwind bit goes really fast. So that might be only like 5 seconds, while I'm hanging and sitting here into wind about 10 seconds. And I'm whipping it around, and I'm sitting there about 10 seconds. And when I say sitting there, like it's just like that straightening out of that turn, straightening out of the turn. So that part of the turn which is still, I'm still turning, but it's, it takes a lot more time than this bit. So this doesn't feel like you're doing nice 360s. Like the thing is the same, the rule is the same, but you feel like you're hanging into wind a lot longer than you're going downwind. If that wasn't clear on this perspective, I try to sort of zoom around that a little bit so you kind of get a little bit of an idea of what that thermal looks like in space. So as you can see, like you look at the bits that were hanging into wind, it's going up, it's going up, it's going up. It's just you're not going very much forward. And like looking from the side, you see how slanted they can get. And these bits are where, where I'm hanging into wind, I'm going up before I whip around and then go back. So how slanted can these thermals get? Quite slanted. You'd be very surprised sometimes. In this case, like I've picked an example of one of my flights where I caught the thermal and where I left it in the end. I had an 800 meter height gain only, over a 10 kilometer stretch. So that's, as you can see, like that's very, very, very flat thermal. It took me 24 minutes to stay with that. And that's 24 minutes of doing exactly that rule that we just discussed, just constantly adjusting for if my vario goes faster, if my vario goes slower, straightening out, fast turn, etc. So that's an average climb of like 0.5 meter a second. So that means like a lot of it is zeros or near zero. Sometimes you can sort of see like there's a little bit of red here and there, which is where you drop out of lift. But a lot of very little lift. You have to work that hard. So you stick with this kind of stuff to give yourself the opportunity to find an area where where it joins with something stronger, which goes up faster, or just to, in this case, to gain 10 kilometers. And again, to find something faster, because if you fall out of this, who knows where you find your next one. All right, then just because we figured the question would come up, which way to turn? In general, neither me nor Guise have ever noticed a difference between turning left or right in terms of how well you turn. Guise has a preferred direction of turning. I don't so much. The one time it is really important that you turn a certain way is when others are already in the thermal. So if you're joining somebody in a thermal, obviously you have to turn the same way. That's just the general rules. And I did find online that somebody claiming are saying, and it makes sense, that if there is a rotation in the thermal, and you can imagine like a bit like a ballerina or like an ice skater, then if the thermal is small, like a willy willy, they rotate really fast. So the ballerina pull their arms in, and when they stretch their arms out, so if the thermal gets bigger, the rotation gets less. So in smaller thermals, the rotation can get faster. If you fly against the rotation of the thermal, then obviously you fly slower, which means you stay in the lift longer and you climb better. I've never noticed the rotation of a thermal, and the only way I think I would be able to tell if I saw debris flying around. Obviously, if you see a bird or another, mostly a bird flying around, like I would probably like follow the bird in the way they turn, because I assume that they know better. But I've never noticed a difference of turning one way or the other. If you feel the wing, if you're flying up to a thermal, as I said before, like sometimes you feel like the lift on one side or the other of your wing, then obviously like it's better to turn that direction if you think that's where the lift is. But when I got sort of instructed on a bit of thermaling, the main point was do not change directions while you're thermaling. While you're working a thermal, you work that thermal, you turn. If you're turning right, you keep turning right. Don't start, you feel like, oh, now I think it's on my left, and start turning left. That's a great way to lose the thermal. A couple of things about how to turn and what sort of turns to make. first thing I wanted to note, something I got told, like your wing or your glider is more stable when you're turning, like there's more pressure in it. So when you're flying through turbulent air, it's actually better to be turning than to be flying straight. Just in case you feel like, hey, this is a little bit bumpy, maybe I should just fly straight and get out of here, rather than use the rules and try to find the core. If you're thermaling, your glider is actually more stable. So stay at it, I would say. All right, about the turns, like the trade-off is like if you do a tighter turn, so if you have a higher bank angle, like you have a faster sink rate through the air, but you do that because it will the staying in like a stronger part of the core will offset that faster sink rate. So like you're still going up faster with your tighter turns. If the day is lighter and the lift is not as strong, then you want to minimize your sink rate as much as you can, and you want to make the turns nice and shallow, a lot of weight shifting, not too tight of a turn. So your sink rate is less. And then the last thing on the turns, obviously it's a bit of a feeling. There is a little bit of a theory going around that a turn should take you about 16 seconds, so you can have a look at your turns there. But when you're sort of established in a thermal, you're only doing very small adjustments, micro adjustments. Don't think about like, oh, it's like a big tug on the brakes. Sometimes if there's a bit of a surge or anything, like you might have some bigger inputs, but your adjustments to adjust from like a little bit straighter, a little bit tighter, a little bit straighter is as small as sometimes a little head movement, a little bit more weight shift, and like a centimeter here or there on your brakes. It's not much more. So you really, like when you're listening to your Vario and you're making those adjustments, like straighten out, tighten up, you really like it's a little bit more like leaning, a little like a centimeter more of the outside brake, like letting it up. And on that, like when I do my turns, like you obviously, or maybe not obvious, when you fly in lift, you slow your wing down. Like you want to stay in the lift as much as possible, so you slow your wing down. So you got a bit of brake on both sides. If I'm turning right, my right hand brake comes on a little bit more, and then generally stays there. And I control my turn with my left hand with my outside brake. So if I need to turn a little bit tighter, I let my outside brake a little bit up. If I need to straighten up a bit, I pull my outside brake like a bit down. So use the outside brake for adjustments, and obviously I can control both with like the inside and outside brake, but I think the outside brake can be more underused. Then you've been working a thermal for a while, and you start to feel like, hey, it gets a bit bumpy, or you don't gain much more height, and you might question yourself like, hey, is this the top of the lift, or am I just losing the thermal? Have I just gone wrong somewhere? And you search around and you find a little bit again, but you might be working the area, and you stay at that level, but you don't really get up higher. That might just mean that you've reached the top. Now, a couple of ways to find out if that's the case, so you don't waste much time there, because if you want to do kilometers, you don't want to waste much time not gaining much height. A couple of things to do is, like, first of all, have a picture of what the expected top of lift is for the day. A couple of apps that we use for that, or like how you can find that out. Guise is a good one that gives you graphs like this, the top of lift for the day, how that builds up. Like in this case, like at 12 o'clock, I cut off the height, but let's say that's about 1500 meters, while like around 3 o'clock, 4 o'clock, it should get up to like, let's say 2,500 meters. So if I launched at 11 and I make it up to 1400 meters high, I know like, hey, this might, and I can't get higher, then I know like it might not just be me, it might just be like what the top of lift is at the time. If you don't want to sign up for XC Skies, you can also use the sounding that we discussed before that you find on Windy, which is a free app. at the bottom you can slide through the different times in the day, and then using the technique that we looked at before, you can sort of guesstimate or get yourself an estimate of how high cloud base / the lift should get at that time of day. Obviously, another way to find out is asking other pilots in the sky, like, hey, what heights are you guys getting at the moment? And if they all say like, oh, I can't get higher than 1400 or 1500, then that might be the lift for the time. Then a quick note, kind of already mentioned it. So the top of lift is not always the same as cloud base. For one, there might not be clouds, and also, as I said, like if the top of the lift, or like the last bit towards the clouds, actually goes with less than like 1 meter, 1.5 meters a second, then you won't get up there, because you don't go, you're going down through the wind, and it's not actually lifting you further. So so those two things are not necessarily the same. Then a couple of sources and triggers that you can look out for. Like, and again, we've sort of focused on the ones that we look at for mostly flying from Bakewell in the flatlands. So a source is where the heats get generated. So the big one is obviously darker fields. So anywhere the fields are plowed, everything around is sort of green fields. The darker fields, they generate more heat. It's fairly easy to, well, you probably get a good feel for it, just, imagining like, hey, if I put my hand on that surface, will it be hotter or cooler than another surface? Most people have can get a fair good estimate there. Same with stony surfaces. So there's quite a lot of like little hills with boulders that stick out. They tend to be warmer. Obviously, if they're in the sun, you put your hand on a bit of stone, like you'll feel like, hey, it's quite a bit hotter than some sand, or like might be hotter than like a grassy field. Slightly protected areas from the wind, as we discussed earlier. If there's an area you can see like that's like sort of protected by trees, or there's time there for heat to build up, that might be a good source. Buildings and sheds. So if you have large buildings, large silos, like a farm with a number of big buildings on it, obviously those tin buildings, like they can start radiating heat quite strongly, as well as towns. The closest to, outside of York, but we fly usually the other way. So obviously Northern, they generate a fair bit of heat because there's all this asphalt, concrete, and that heat needs to go somewhere, which is up. Then some triggers. So we use triggers. We kind of conflate two things, and we call them both triggers. So one is a point where the thermal releases from. So we're looking at like high points in the terrain. So hot air sort of like creeps up but sticks to the ground, and like obviously like the most likely for it to sort of pop off somewhere is at the highest point, which is also why tree lines are a good trigger point or a release point, because if the downwind tree lines in particular, if a field of hot air before the tree lines, that bubble of hot air gets sort of like pushed towards that tree line, and it gets higher and higher closer to the tree line. That tree line is probably where it reaches like a threshold, and it starts to pop up from there. So the tree line becomes the release point. Lakes and dams. So dams in particular are very consistently good, I found, when flying the flatlands. I think they have like a similar mechanism. Like a dam obviously has the same sort of thing as a high point. Sometimes they're in a field and they just build up, and that's just the highest point in the field. But both lakes and dams, if there's water in it, the water is cool. The air above that water is a little bit cooler. So if the wind blows that cooler air underneath the hot air around the dam or the lake, that means that like sort of like works as a wedge, and that wedge pushes the hot air up, and then because it gets pushed up, like the inertia takes it further up, and it's a great release point. But also things like sheep and like machinery going around are really good release points. So example for dams, for instance. So I found an example in my track logs, getting low here in on my flights. I'll zoom in a little bit. So a dam there, fairly easy to spot when you're flying, a bit harder when you go this way. So I'm getting low. I'm flying downwind, obviously. So like I expect the thermal to release from like the downwind end of that dam. And so I'm flying straight over it, and truth nuts, I'm getting something straight after. Another good one are farms. So especially if they're built on a hill, which seems to be like quite a normal thing to do. So like you've got some farm over here, and this hill, this is actually a little bit higher. So like this is a nice and dark field. Another shed over there that gives us like a couple of trigger points, as well as this whole field. If that builds up, it all sort of like the heat sort of like drips uphill, if you want, towards that farm, which should be like a nice trigger. As a little bonus, this dry riverbed, if the wind blows the hot air from that field towards that riverbed, I've got a second chance to get another thermal there. I caught a thermal which looks like on this picture like it's after that riverbed, but it's actually well before that, which is coming from that dam or from that farm, and I'm catching it up and save myself from a bomb out in that location. Now this is not a very good example in terms of how you should fly, because I'm getting low before northern, and I'm going on a glide towards the ovals, thinking like if I don't catch anything, I'll just land on the ovals. But like on my glide, I actually realized, I'm not even sure if I make it. And I, instead of turning around and landing outside of town, I went in with fingers crossed, and I'll assume I'll catch something on my way up, or catch at least a little bit of lift, so I can still make it to the oval. And indeed, I caught like a nice thermal there. So obviously make sure if you're flying over a town that you can always glide outside of town to land, or you see proper landing options. But towns are pretty good, very good triggers. Northern in particular, and this is something I found, and not sure if others have the same experience, but my theory is that since Northern is such a good source, you get often like strong thermals above it, which means that just outside of Northern you get a lot of air going down. So I feel there's a bit of a sinkhole like just outside of Northern. So I either will fly over Northern if I'm if I'm fairly low, fly over Northern, or well outside Northern. So on the right I would go as far as like sort of like Grass Valley, unless I get a boatload of height well before Northern, then you can fly over the trouble area. And then we've got some there's a picture from Jockey Sanderson video, who did a video on like farm machines. So like we got plenty in the flatlands behind Bakewell as well. Just didn't have a good example, so I stole one. If you see machinery like in a field that like looks like it could be a good source, definitely worth flying over that, because they are likely to disturb the hot air enough for it actually to release and go up. And then finally, rivers and tree lines. Kind of mentioned this one already. When I was flying here, like coming downwind, and obviously like this field was a bit darker at the time of flying. You can sort of see that Google has a line here with what it looks like when it's not green and what it looks like when it is green. But anyway, so it was nice and brown when I flew there. Wind is coming from this angle, so I figured like all the heat that's building up in this field gets pushed onto this tree line / river, so it will probably release from that corner, because that's where it builds up most, because everything sort of pushes it into that corner. And indeed, like when I got over that, like you get a nice climb out from that point. And then finally, some tips and tricks to spot a thermal, and these are like some of the most basic ones. So, but we hadn't had them anywhere in the presentation, so I just want to make sure that we do mention them. It was embarrassingly long for me to actually look at rustling patches in the greenery on the hill to spot where the thermals are. So while I had heard the theory before, I never actually did it in the beginning until it was actually Wayne, I think, that said it. Like, I look at the rustling patches, and when I did that, I was actually surprised like how clear it is to see, like, hey, everything's pretty calm, and like, hey, but over there's some proper rustling going on, and you fly there, and that's where the thermal is. So definitely worth doing. And then Guise told me, like, he does a lot of that when he's on XC as well. In a field, you can see the same patches, and I'd never really looked at that. I always look at my sources and my triggers, and then fly over those. And I've never actually taken the time to look at trees or fields in the area to see if I could actually spot the thermal. So we'll start doing that from now on. Obviously, if you see other pilots going up, that's a clear sign that there's lift there. If you see birds going up without flapping their wings, that's a clear sign. And if you see material flying around, so if you see grass flying around, obviously there's some thermals there. If you're flying and you start smelling some ground smells, then they must have been brought up by a nearby thermal. So definitely worth maybe slowing down and searching the area. And we already mentioned that once you stand on the hill and the sounds start from the town start to be more pronounced, that means the thermal is blocking the wind. So get ready to take off, because hopefully the thermal is making its way slowly towards the hill. If you can take off like into it, like the earlier the better. A couple of mindset things when you're flying and you get heavy sink. Like when I early on flew, I was getting a little bit like pissed off because this is heavy sink, like I'm going down, like I worked so hard to get up. But you have to realize, like, hey, the sink is necessary for me to get closer to another thermal. So flying through heavy sink is a good thing, as long as obviously it's followed by you hitting that thermal. When you start going from a smooth glide to a bumpy one, same sort of thing. Instead of, in your head going like, oh, bumpy means collapses or, potentially dying. No, it's because like you're getting a bit of turbulence because you're getting close to a thermal. You get close to some activity. So it's a good thing. So stay on the positive side and, find that lift and put the theory into practice. All right, that was the presentation about thermaling that we went through yesterday. And we've got another presentation coming up that puts all of this into a little bit more practical stuff, where we talk about like cross-country paragliding, how to prepare for a cross-country, how to prepare a route, your instruments, and the practical side of flying, really. Looking forward to see everybody there on the evening. If you're fairly new to paragliding, you're more than welcome to meet some people to get this information. If you have been flying for quite a while and you're quite experienced, then by all means come along as well, because for one, there might be something in there that you can pick up, but two, it's also great for you to share what you've learned with some of the newer guys. And I know from experience, I'm a fairly new pilot myself. I've only been flying for just about 2 years, and I very much appreciate it, especially in the beginning when the more experienced guys were willing to share their knowledge with myself and with others. This helps to progress like faster. So by all means, would very much like everybody to come to those evenings, if nothing else, just for the pizzas and beer we put up. And of course, we'd like to see you all on the hill to go flying. So I know like on the hill, it's not always the best time to share that knowledge, or, like if we want to go for a long flight, we're just eager to get off the hill. And it's a bit harder to get people to help you out, or to give you more information, or to set up your stuff. So it's better to come prepared, have it all ready to go, and on the day itself you can come fly along. So see you all in the next evening. Thank you very much for listening. Any comments or like additions are very much appreciated. And looking forward to see you all in the hill and in the sky. Fly safe.